So this is just a quick video that I wanted to make to show you guys to clarify how to actually do these Hess's Law's problems. So Hess's Law is basically stating that the enthalpies of a reaction are a state function, which means that I only have to concern myself with the beginning products and the end products, and it doesn't matter anything else that happens in between. And because it doesn't matter what else happens in between, just like a system of equations, I could use a system of chemical reactions to allow me to calculate the enthalpy, the unknown enthalpy of a given reaction if I have a system of reactions that have similar reactants and products. So in this example, I'm being asked to calculate the enthalpy of the reaction for at standard temperature and pressure. That's what this little circle means. Given these three chemical reactions. So basically what I'm trying to do is figure out how I can manipulate these equations to give me this equation so that everything that's not in that equation, everything that's not in, I'll call it the main equation, right, which is this one here, is going to cancel out. And the only way I can do that is by either multiplying, by flipping, and that's pretty much it. So I could change the stoichiometric coefficients, or I could change the direction of the reactions. So the first thing to do is to look in the other reactions, so these systems of reactions that I'm given, and figure out where the overlap is between these equations and the equation that I'm being given. So for example, C2H2 is found in the products of the main reaction, but it's in the reactants of the first equation. So I need to get this from the reactants to the product side, and the way to do that would be to flip it. Okay, so that one is going to get flipped. I'm going to write flip. So I'm in Austin at my niece's birthday party, so I'm doing this without my equipment, so I'm just going to write that as best as I can. So when I flip that, now I'm just going to ask you to bear with me and imagine that all this stuff that's on the reactant side is now going to be on the product side, and all the stuff that's on the product side will be on the reactant side. Okay, so if I do that, that will give me C2H2 on this side, which is where I want it. But if I look at the rest of the stuff, so the water, the CO2, and the oxygen, I don't want any of those things. So I need to find a way to make those things cancel out using my remaining two reactions. Okay, so let's look at the second reaction. So the second reaction has two things that I want. The first is that it has carbon in the reactant spot, just like I have carbon in the reactant spot in my main equation. The other thing it has is carbon dioxide in the product side. So this is useful because remember, this carbon dioxide that I want to cancel out in the first equation is now going to be in the reactant side. So in order to get the stoichiometric coefficients to match up, right, I have a 2 in front of this carbon. I'm going to multiply this whole equation by 2. So I'm going to get 2 carbon plus 2 O2 gives me 2 CO2. And that gives me two things again. So that's going to allow me, I'm going to underline the things I want to keep, which is the 2 CO2 and then the C2H2, which remember is now going to be on the the product side. And it also lets me cancel out this 2 CO2 over here. So you may be thinking, just in case you forgot, how does this CO2 cancel out with this CO2 when they're both on the product side? But remember, we flipped this equation, so this one is now on the reactant side and this one is on the product side, so they can cancel out. But I still have a problem, right? So in the first equation, I still have this 5/2 O2 and this water that I need to get rid of. And in the second equation, I have this 2 O2 that I need to get to cancel out. Okay, so let's look at the last equation. So the last equation, again, has something that I want. It actually has two things that I want. So it has the hydrogen gas, H2, which I need for my main reaction, so I'm going to underline it, and it has the right stoichiometric coefficient. So that suggests to me that I'm not going to want to do anything to this equation in terms of multiplying it. It also has the water that can cancel out with the first equation. So water here is on the reactant side, because remember we flipped it, and water here is on the product side, so they can cancel out. So now let's look at what I have. I have the 2 carbons, which I want for the 2 carbons. I have the H2 gas, which I want for the H2 gas over here. And when I flip this equation, I have the C2H2 gas, which I want on the product side. However, I still have this 5/2 O2, this 2 O2, and this 1/2 O2. And if you remember, when we flip the equation again, the 5/2 O2 is actually on the product side. So I basically have 4/2, right, because 2 is the same as 4/2, and 1/2, which gives me 5/2. So the two of these sum to give me 5/2. And those are on the reactant side. I have 5/2 on the product side, so therefore those oxygens can cancel out as well, which is good because that means that I've recreated my primary equation. So I have the 2C2, I have the H2 gas, and I have the C2H2. Now the question is, how does everything that I just did here actually allow me to calculate the unknown enthalpy? Well, I'm just going to do to the enthalpies exactly what I did to each of the equations, which means for the first one, I'm going to flip it. So instead of negative 1229.5 kilojoules, it's going to be positive 1299.5 kilojoules. And for the second one, instead of 393.5, because I multiplied this equation by 2, I'm going to multiply this equation by 2 as well. And for the last one, I'm going to leave it exactly the same as it is because I left it exactly the same as it was. So let me do that math real quick and find out what the negative 393.5 is. So I'll bring up my calculator. So using my calculator, it doesn't want me to be able to see it. Move this over. No, apparently you can't move it. So using my calculator, hold on, let me pause this. Okay, so I went ahead and did that in my calculator. So remember, I flipped the delta H for this one because I flipped that reaction. So I take positive 1299.5 kilojoules. I add negative 787, because remember I multiplied this one by 2 in order to get those numbers to cancel out. And then the last one I left it exactly as it was. So I add those three numbers together, and when I do add them, I get 226.7 kilojoules. But remember my sig fig rules, so I'm looking at the decimal point, so this would be 227 kilojoules. Okay, so I rounded to 227 kilojoules, and that is my answer. So again, what did I do? I looked at my main reaction, I looked at my system of reactions, and I said, what can I do to get the stuff that I need to keep to give me this reaction to stay, and the stuff that I don't need in my main reaction to cancel out? And my two options are to flip it so that the things that are on the reactants are in the products, in which case I flip the sign on the delta H, or I can multiply the entire reaction by some new stoichiometric coefficient, which would get multiplied across the whole reaction, and then I would do that same multiplication to the delta H. Once I get everything that I don't need to cancel out and everything that I do need in the right place, I'm then able to add up all of my reactions, and that gives me my final answer. Okay, so this is Hess's Law, and we're going to do a few more practice problems on Monday, but this should hopefully help clarify what I was doing on Friday. Sounds ranting. Okay, so hopefully this helps, and have a good night.